Yeah, please play the pre-record video. Thank you.
Hey there, welcome to my talk. My name is Han Qiu. I'm currently a software engineer at Waymo, working on perception and mapping. In this talk, I'll present some of my work on cooperative perception before joining Waymo. Towards the end of my talk, I'll give an update on our recent release of Waymo Open Dataset and the challenges we're hosting this year. To get it started, let's put on our driver hat for a second and imagine in this scenario, we're driving a single road where there is a double parking truck blocking our way. Self-driving cars are equipped with 3D sensors, such as LiDARs and cameras, to sense the environment. However, just as human eyes, they provide no visibility behind occlusion. For example, in this point cloud I'm showing here, the LiDAR cannot see anything behind the orange truck. So what this means is that the autonomous driver will be uncertain about what to do, and any risky maneuver could cause severe crashes. So for example, here, the black vehicle make a lane change maneuver and could crash into the upcoming traffic in the opposite direction. These scenarios are not very uncommon. Here are a couple more examples. Again, we are in this black Eagle vehicle. We're trying to turn left. There, in the opposite direction, there is also a left-turning truck blocking our view of this red car. We call it collider. Here, making a left turn could cause a crash. Another example, our Eagle vehicle here is going straight with a green light, and there is a sequence of vehicles waiting to turn left on our left side. And at this moment, there is a car rushing a red light and came out of the last orange truck, making it no time for us to brake. Cooperative perception can solve this problem. The idea is that we can share what the front car can see to the car behind, so effectively the car behind can see through the obstruction and see the upcoming traffic in the opposite direction. To better understand this and what this means for self-driving, here's a short demo video. So cooperative perception enables other vehicles to share what they see to the Eagle vehicle so that the Eagle vehicle can brake ahead of time to avoid the crash. Back in 2018, we have showcased this capability in a real-world prototype, demonstrating that it is physically feasible to achieve see-through capabilities through wireless communication. We have demonstrated it using point clouds from both the reconstruction from the exterior camera and LiDAR. Here is a teaser video showing how we did it in the old days. We first created a 3D map using SLAM. Here we're using ORB-SLAM 2. And all the green dots are the ORB features that gets registered into the map, showing the red dots on the left. With the map now, both the cars can localize themselves with respect to the map's coordinate frame of reference. And here I'm showing the 3D point cloud reconstructed from the stereo camera. On the front car, the leader's view is showing on the top, follower's view on the bottom. So when the leader transmits objects to the follower can merge them into its own perspective and create an extended view shown on the top and the original view shown on the bottom. Here you can see the occluded and out-of-range objects are now visible. Recent years have seen many cooperative perception work. For example, V2VNet, published in ECC-V20, enables sharing intermediate representation from convolution layers and uses a graph neural net to enable representation aggregation for perception and prediction. V2X Vision Transformer proposes to use a vision transformer to aggregate information from both vehicles and sensors from the roadside infrastructure. CoBVT leverages multi-agent, multi-camera, bird-eye view fusion to make real-time map semantic predictions. In the wireless community, there are also a couple of works that discuss how to enable early fusion of point cloud and late fusion of bounding boxes using vehicle-to-vehicle communication and vehicle-to-infrastructure communication. In all this work, they were able to demonstrate that peer vehicles can provide additional vantage points to make previously invisible objects visible. Now, beyond object detection and map semantics, our recent work, CooperNet, takes another step to investigate how cooperative perception can help improve end-to-end driving behaviors. Specifically, CooperNet answers the following question: can we learn from the shared scene representation the useful information to guide our driving decisions? Here is an overview of the problem. Given that we have V2V communication, which we can use to transmit representations or encoding information about LiDAR and potentially metadata such as pose and velocity, the goal is to come up with an ego-vehicle driving policy by analyzing the shared information. Such policy can be potentially generalized to multi-agent policies that embed negotiations and collaborations implicitly. CooperNet tackles the end-to-end ego policy learning first. Each cooperative vehicle encodes its LiDAR data into a compact representation of, let's say, 128 features, each one with 128 bit of embeddings and an extra 3 bit of XYZ location. We use a point transformer for the encoding and use voxel pooling and downsampling to reduce the message size. At this point, for the cooperation to go both ways, the ego car is no different than a cooperating vehicle. It's totally symmetric as it also encodes its own LiDAR into the same contact format. And then what differentiates an ego vehicle is that upon reception of shared messages, it does spatial transformation using the XYZ and relative pose, transforming features into its own bird's-eye view perspectives before doing the voxel pooling to further merge and downsample. Finally, the features are merged with ego vehicle's features through a point transformer aggregator to output control decisions. The CooperNet model is end-to-end trainable. We collect an expert trace dataset and use behavior cloning plus Dagger to train the model. During the cloning, throttle loss weight is tuned down to give it a little bit more focus on brake and steering. The expert in this case is a very simple path planner. It has two modes, no sharing mode and sharing mode. In the sharing mode, it has global ground truth information such that it knows every traffic participant's location, velocity, and future trajectories. No sharing mode expert is for baseline training. Here is a recap of the scenarios where we evaluate a CooperNet performance: overtaking, unprotected left turn, red light violation. So in each of these scenarios, there is a black vehicle, we call it ego vehicle, whose view is blocked by an orange truck, and the red car is a potential collider behind the truck, and therefore invisible to the ego vehicle. So here is a video showing how CooperNet and no V2V sharing perform driving decisions. So on the top is the bird's eye view. On the bottom is showing the LiDAR. On the right bottom shows the merged LiDAR. So CooperNet in this case was able to wait for the opposite car to pass by before making the lane change maneuver to overtake the double parking truck. In the left turn scenario, CooperNet is aware of this upcoming collider, shown here on the bottom yellow circle, so that it waits until the car passes by to make the left turn. In the red light violation scenario, similarly, because of the sharing from the orange truck's perspective, the eco vehicle is aware of this upcoming red collider. So it brakes really early and wait for the car to pass by and accelerate to cross the intersection. So here are some numbers. We compare CooperNet with multiple baselines, no V2V sharing, early fusion, and voxel graph neural net. So you can see that no sharing mode performs really poorly, especially in these three scenarios, and any cooperation could actually help. And compared to cooperative schemes, CooperNet outperforms early fusion and voxel GAN baselines. So this all looks amazing. The next question is, how do we deliver this capability to every vehicle? It is very challenging to scale this capability to every vehicle in need. Suppose we have a busy intersection like shown here, and for example, we know some of traffic patterns. H is trying to turn left, A is trying to go straight. C can tell H about A's position and velocity, so H can make the decision. Symmetrically, C is turning left, I is turning right. H can tell C about I's information. More sharing could be happening. F could be telling I and C about the pedestrian's information. A roadside unit could be telling L about the traffic light signal phase. So as you can probably imagine already, making cooperative perception available is a very challenging system problem. To make all of this happen, we need to enable them for dense traffic scenarios with very limited wireless bandwidth and short latency to meet decision deadlines. Our recent work, AutoCast, addresses these challenges by carefully analyzing the situation and scheduling who should transmit what at which time, so that with limited wireless bandwidth, every vehicle can still leverage the shared information to augment their vision. Shown on the bottom right here, each vehicle A, C, H, J can have their own perspective merged with shared information. So before diving into details, let me give you a 10,000-foot overview of the AutoCast architecture. When 3D frames come in, it first goes through a spatial reasoning module where we analyze objects of interest, and then vehicles communicate metadata about current frame through the control channel with other vehicles. Once they get other vehicles' metadata back, they can run the distributed scheduler. Following the schedule, each vehicle shares their sensor data via the data channel. Finally, fusing shared data, the planner plans the trajectory and issue control decisions. So the whole architecture is divided into two planes, a data plane and a control plane. The data plane contains spatial reasoning, trajectory planning, and sensor exchange. The control plane contains metadata exchange, where we share pose, trajectory, detected objects, and occluded area information. It also contains the scheduling part. Now let's dive deeper into each one. First up, object of interest. Here we do spatial reasoning and occlusion visibility analysis to address which object is relevant to which receiver. To give a very high-level idea, AutoCast converts point cloud into occupancy grade by voxelizing the point cloud and classify the grades as empty, ground, and object grades. And then it can determine a visible area by tracking those empty grades behind objects. Then after receiving the same visibility information from other vehicles, it determines whether detected objects are relevant to its peers. Next, I'll talk about the orchestration and scheduling problem. For orchestration, we send periodic control messages or beacons, which contains planned path, detected objects, and which implicitly include the invisible area for each transmitter's perspective. Now, combining all the information, the scheduler can make a final optimization. We formulate the problem as the following. Suppose we have V vehicles, O objects, and C type of representation. And let's define Xijk as the indicator of vehicle I sharing object J in representation K. And let's define WPJ being vehicle P's interest in object J. For example, here, H would be interested in A's position, so WHA would be 1, and WCA would be 0, because A is visible in C perspective. So WPJ is actually defined based on the visibility and trajectory from beacon. Now we formulate the optimization problem to maximize the total rewards of any representation of object, combining the object's total interest from all the receivers. Each object need only be transmitted in one representation. And the total time of transmitting all the objects should be less or equal to the total time of the scheduling. Now, there are standard optimal solution for this problem. Suppose we have 40 vehicles. It takes 10 minutes to solve just one round of iteration. And if we use dynamic programming, it takes about 3 seconds. This is still too long because we want this kind of scheduling to happen at 10 frames per second. So we did a greedy optimization. We rank all the objects or features by the rewards over the time to transmit that feature or object. And then we transmit the highest rank object or feature first. So the greedy algorithm only takes 0.06 seconds to finish, and the performance is very close to optimal. Finally, we used the combined information to do trajectory planning and object avoidance. I'm going to skip this planner part because we talked about using this as the expert in CooperNet, but I'll show you some planning results in the final demo after evaluation. So we have done a thorough evaluation, randomizing the various background traffic and the collider speed in all 3 scenarios. We compare AutoCast results with all kinds of different baselines. One notable baseline here is the purple, which is unlimited, that allows unlimited sharing of information without considering any latency delays. This figure shows that AutoCast is very close to the unlimited bar, eliminates crash and undesirable deadlocks and near misses in all 3 scenarios. This slide focuses on the evaluation of the scalability. The y-axis is showing the safe passage ratio on the left and the collider visible time on the right. Because of the careful design in choosing what to share, AutoCast can scale gracefully to up to 40 vehicles and still achieve near optimal performance. We also experimented with real V2V communication radios, mounting them on the cars to collect data. Our experiment validates that the assumed bandwidth in the simulation can be achieved in the real world. We also optimized the whole AutoCast stack, from quantization to path planning and object avoidance, to be able to operate at 10 frames per second using a regular laptop. Here is a video showing AutoCast operating at scale when there are a lot of different cooperating vehicles sharing around one intersection. So you can see the path planner now is planning the path with a receding horizon. The green one is closer in time. The blue ones are farther out in time. So a bit of summary here, I've talked about AVR, which is a real prototype that demonstrates the feasibility of cooperative perception, CooperNet, an end-to-end cooperative driving agent, and AutoCast, a scalable communication framework. This is just the beginning. In the future cyber-physical system, there could be more ML-empowered devices, such as drones, cameras, and wireless roadside units. How can we enable all of them to collaborate while doing their own tasks? A second question we can ask is, what is the best way to ensure the robustness of this collaboration? Finally, what if there is a malicious drone sending wrong information? How do we stop it from disseminating? These are very interesting questions to address before we can build such an intelligent and collaborative ecosystem. In the next few slides, I'd like to switch gears a little bit and take this opportunity to give an update on our 2023 release of Waymo Open Dataset. This is a joint effort with many contributors and partners from many cross-functional teams across Waymo. Ever since the first release in 2019, Waymo Open Dataset has been through many iterations and hosted 3 challenges. Till last update, we have formulated into 2 separate datasets, Waymo Perception Dataset and the Motion Dataset. The Perception Dataset has 2,000 scenes with sensor data and high-quality labels that enables evaluation of tasks such as detection and tracking. The Motion Prediction Dataset has over 100K segments with object data without no sensor data. This year, we are adding raw LiDAR data to the motion dataset. Because of the addition of raw LiDAR data, the motion dataset becomes an end-to-end motion prediction dataset. In the meantime, we're also adding map data to the perception dataset and making it a more modularized dataset for more flexibility. We're offering 4 challenges this year: 2D video panoptic segmentation, pulse estimation, motion prediction, and same agents. In the next few slides, I will quickly go over what's exciting about each challenge this year. Starting with the panoptic segmentation, we have a per instance semantic labels across 5 cameras, which constitutes a panoptic view. The instance labels are consistent across all images in the sequence and all cameras. In the post-estimation challenge, given one or more LiDAR range images and associated camera images, the task here is to predict 3D key points for pedestrians and cyclists in the scene, up to 25 meters from the autonomous driving vehicle. We have offered high-quality 2D and 3D labels, very large suite of evaluation metrics, and first, the semi and weekly supervised learning of human pose in the wild of such scale and quality. For motion prediction, given the agent tracks for the past 1 second on a corresponding map and the associated LiDAR data for this time interval, the task here is to predict the position of up to 8 agents for 8 seconds into the future. Because of the addition of LiDAR data, this is 100x more LiDAR points released than the previous perception dataset, making it the biggest LiDAR release of Waymo open dataset up to date. Previously, motion planning is using perception output, for example, a sequence of bounding boxes for each object being tracked. Such representation often loses a lot of context of and around the object. Offering raw point cloud data can address this problem in motion prediction. Here are some segments that we release on top of existing bounding boxes. We can see the LiDAR from all the LiDAR devices on the car. We believe end-to-end learning using raw data can compensate for object detail lost from bounding boxes. In fact, our early experiments show that end-to-end learning can boost the motion prediction performance by quite a bit. Here, I'm showing some different output using LiDAR or not using LiDAR. For same agents, similar to motion prediction, given the agent tracks past the 1 second on the corresponding map, and optionally the associated LiDAR for this time interval, the task here is to simulate 32 realistic joint futures for all the same agents in the scene. So we're offering closed loop evaluation of agents, which is very useful for autonomous driving testing and in simulation. So the challenge is live until May 23rd. So if you have a brilliant idea or have been working on relevant projects, welcome to participate in the challenge and compete for the award. That's all for the update. Thank you for your time.
Okay, thank you for the talk from Hongqiu.